Hi, it's my pleasure to give the university Distinguished Scholar Lecture this year. My name is Deng. I'm professor of environment engineering at Montclair State University, Department of Earth and Environment Studies. Here, I'm directing the Water Innovation, Sustainability, and Engineering Lab. Today, the title of my talk is Innovative Solutions to Water Challenges. So let's start with this graph. I believe most of you have seen this graph before. This is the natural water cycle. It tells us water can transform between different forms, but the mass keeps constant on a global scale. But I would like to highlight here that is a natural water cycle. If we consider human activities, we have to modify the systems. Water is important to us. Unfortunately, less than 1% of Earth water is directly available to us, including rivers, lakes, groundwater, and wetland. Every day, United States withdraw 322,000 milligallons water from the nature. We use water for 8 different categories. On average, every person in the United States takes away 1,006 gallons water from nature. On the other hand, water is subject to pollution. We have different pollution sources. One type is called point pollution source. For example, like here, we can see this graph just shows you the different pollution sources to groundwater. We can see like linking underground storage tank. It just releases gasoline into the groundwater, make pollution. That is one example of point pollution sources. Also, we have another type, it's called non-point pollution sources, particularly for runoff in urban and agriculture areas. We have different types of pollutants, chemical, physical, or microbial. So I would like to show you one subsistence of water cycle to discuss where we are working. That is urban water subcycle systems. Why are we interested in urban? Because 82% of American people are living in urban areas. For New Jersey, where we are, more than 90% of people are living in urban and metropolitan areas. So look at the graph. Left side, we can see left side that it's natural water systems, including stormwater, groundwater, and surface water. We can see interactions between each component. On the right side, we can see we can withdraw the water from nature and build water treatment plant. And then we improve water quality to drinkable level. We use water and then send the wastewater for treatment. One way is to treat on-site, like septic tank systems. Another way, much more popular, is centralized treatment systems. We use the sewer systems to collect wastewater and send it to wastewater treatment plants. After treatment, we send the treated wastewater back to nature. So we close the loop. For many states, without enough water resources, they encourage water reuse, such as California, Texas, and Florida. So we can reuse water for non-potable purposes, for example, car washing or toilet flushing. Or we can send the treated wastewater back to water treatment plants as part of drinking water sources. Besides water production, we generate huge amounts of wastes. From drinking water treatment plants, we produce water treatment residue, WTR. It's mostly metal hydroxide. After treatment, we send it to landfill for disposal. Sewage sludge produced from wastewater treatment plants. It's sent to lab application or incineration facilities after certain treatment. Please pay attention to landfill, because landfill is part of waste management systems. But after precipitation, rainwater can infiltrate into landfills and make highly polluted wastewater. It's called landfill leachate. For old landfills, leachate can directly go to groundwater and make pollution. For example, New Jersey, 25% of Superfund sites in New Jersey were polluted by landfill leachate. Superfund sites are the most contaminated sites in this country. For modern landfills, we have collection systems. We can collect landfill leachate for treatment outside. In most cases, in New Jersey or many other states, we send landfill leachate to local wastewater treatment plants. So it will be mixed together with sewage for treatment. So landfill leachate plays a key role to bring municipal solid waste, that's trash contaminants, from waste to water cycle. For example, PFAS, that's one emerging type of persistent organic pollutants. So my lab is working in drinking water treatment, landfill leachate treatment, wastewater reuse, and stormwater management. The goal of my lab is to use chemical and physical principles to mitigate contaminants in different engineering systems, different environment systems, particularly water, including drinking water, municipal and industry wastewater, polluted groundwater, stormwater, soil, and sediments. We want to achieve environmental resilience and sustainability. We want to protect human and ecosystem health. The major approach of my group includes advanced technologies, innovative designs, and sustainability strategies. Collaboration is key. We build strong collaborations with our collaborators here or from other countries. Their background spans across different fields, from chemical engineering, material science, environmental chemistry, economics, to social science. So here I would like to share some of my research with you. We have two major research areas. The first one is innovation in water treatment. Innovation is to create and perform new processes, new methods, and new products to significantly improve quality and effectiveness of water treatment outcomes. We have extensive investigated in different treatment methods, such as advanced oxidation and reduction processes, Ferret-based technologies, adsorption, nanotechnology, distributed and household water treatment. We use these tools to address traditional contaminants, such as particles, oxygen-demanding materials, nutrients, and other traditional pollutants. As well, we focus on removal of emerging contaminants, like PFAS, like pharmaceuticals, and personal care products. Okay, so here, let me just briefly introduce two of my major research areas. One is Ferret technology. Another one is household water treatment. Particularly, I will discuss the household water treatment for emergency water supply after natural disasters. Ferret. Why ferret? And what is ferret? So this is a chemical structure of ferret. We can see ferret is anion. It has 1 iron and 4 oxygen. So iron has an unusual oxidation state, 6+. Ferret can be combined with sodium or potassium. That is crystal, it's purple crystal. Once we dose it into water, water is purple. After treatment, the purple color is gone, and we get sediments. That is iron sludge. Ferret's manufacture was first reported in 1700. Until 1960, ferret was only investigated in the field of chemistry. In 1970s, ferret's potential application to engineering purposes was proposed. After almost 10 years, ferrets for water and wastewater treatment was reported. Why ferrets? I think at least ferret has 2 unique properties. Number one dose can achieve multiple functions. We just need to add 1 dose of ferrets. We can do chemical oxidation, we can do disinfection, coagulation, precipitation, and absorption. Chemical oxidation can decompose organic pollutants. Disinfection can kill microbes. Coagulation can remove particles in water, let water clear. Precipitation and absorption can remove dissolved contaminants, such as arsenic or phosphate. Second, ferret is safe. Different from other water treatment agents, for example, chlorine or ozone. Ferret does not produce any unwanted byproducts. If we dose ferret in water, we can see the system is pretty complex. Many reactions occur in parallel or sequentially. But if we can improve the understanding of ferret chemistry, we can make the best use of the systems to remove contaminants from water. So here, I just give you one example. Harmful algal bloom, that's eutrophication. We know if the water has too much nutrients, phosphorus and nitrogen, they can support the crazy growth of algae in the water. It's called eutrophication. Eutrophication particularly occurs in the summer. So eutrophication can bring a lot of negative impacts. For example, it can dramatically increase cloudiness because of too many algal cells. It also can quickly deplete oxygen in the water. Fish will die, and water becomes stinking. Also, some algae can release highly toxic chemical. We call algal toxins. So here, I just give you one example is like the lake Hopatcon that is the largest freshwater lake in New Jersey. This lake has suffered from eutrophication over the past years. It was even closed because of the water quality degradations. In fact, more than 50% of rivers and lakes in the United States suffer from eutrophication. So here I show you some data regarding ferrets removal of different contaminants in alga bloom impacted water. So we can see here, this is alga bloom impacted water. It has high concentration of alga cells. It's clouded. Inside, we have alga toxins, trace contaminants, highly toxic. So if we add ferrets into the water, number one, ferret can oxidize alga toxins, transfer them from toxic compounds into less or non-toxic chemicals. Number two, iron 6 is transformed to iron 3, that is what? And neutral condition, that is iron hydroxide, is rust. It can capture alga cells to increase the density of cells and let them sit down by gravity. Water is clear. Moreover, when ferrets decays, it will release oxygen. So it can increase dissolved oxygen in water. So we can see after treatment, the upper water is clean. And we just use one dose of ferrets to deal with multiple problems in alga bloom impacted water. So here I show you more data here. X-axis is ferret dose. And we have a different Y will dramatically alga toxins drop down. Alga toxin is the diamond here. This diamond here quickly comes down here. So here we can see flow cam images very clearly. We can see iron hydroxide capture alga cells to increase density. So allow the particles to sit down quickly. Okay. Before, many other groups also investigated ferrets. But the major idea is to use ferrets as additional treatment for the traditional water treatment plants. Just try to help or improve water treatment quality. So look at here. This is a flow chart of traditional water treatment train. It's pretty long. It's composed of different treatment reactors. Each reactor is designed for one specific purpose. For my group, different from others, we propose, why not? Just use a ferret-based reactor. We can use one to replace all. We just borrow one concept, important concept from chemical engineering, that is process intensification. That means we just combine different units into one. We can reduce the space requirements. We don't need to hire too many people to operate the systems, but we still can achieve similar, equivalent, or better treatment performance. So that's what we are working now. So here I just give you one example to show you how we use ferrets to achieve removal of multiple contaminants in water. That is emergency water treatment after natural disasters. United States has been ranked number 2 among the hardest hit countries by natural disasters. For example, 2017, we had many natural disasters. 3 major hurricanes made landfalls. Hurricane Harvey, Irma, and Maria. At the end of 2017, there was wildfires in California. In the whole world, in 2017, total economic loss due to natural disasters was $334 billion. During or after natural disasters, water is one of the three basic demands. We need water for what? Number one, drinking. Number two, cooking. Number three, hygiene. So that means we need water for survival and disaster relief. At least each person, and this extreme condition, each person needs 15 liters water every day. FEMA recommends 3 emergency household water treatments: boiling, chlorination, and distillation. Unfortunately, in most cases, they are not effective or feasible. So here I just give you one example to show you the challenges of water treatment after natural disasters. This is Puerto Rico after Hurricane Maria. Hurricane Maria made landfall on September 20, 2017. It was Category 4 hurricane. So just after landfalls, around 50% of Puerto Rican people did not have water supply. 2 months later, we can see still 9% of people did not have water supply. That means over 300,000 people there. Look at the survey for the water after Hurricane Maria in Puerto Rico. 21% say, I drinking the water from the nature. That could be river water, could be well water, could be runoff without treatment. Half of the people say, we do not have enough water for drinking. More than 50% people say, I was worried about the water quality. After hurricane, power outage. So our treatment systems cannot work. And also the pump cannot work. The pump cannot work means we cannot transport water from treatment facilities to end users. Many pipelines are damaged, and road systems are also damaged. Plus fuel shortage and curfew, making the water transport from here to there extremely difficult. On the other hand, high temperature. Every day is summer in Puerto Rico. So the water demand is extremely high. So here I just show you some of the news from different social media, newspaper or website. We can see the people try to find any containers they have to get water from anywhere. So just after Hurricane Maria, our group thought, why not Ferret? We just collect some river water with those untreated sewage. We simulate polluted natural water. And then with those ferrets, this graph shows you disinfection performance. X-axis is ferret dose, and y-axis is the log reduction of microbes. 1 log reduction means 9% removal. 2 logs means 99%. 3 logs means 99.9% removal. From here, we can see we just need 3.0 milligram per liter ferret. We can remove more than 99.9% of E. coli and total coliform. At the same time, we can remove different toxic heavy metals. For example, copper, zinc, cadmium, lead, and arsenic. Same, if we increase the ferret dose, we can see we can remove more toxic metals. Also, ferret can achieve coagulation to remove particles. Let water clear and transparent. So with increasing ferret dose, we can see the turbidity here quickly decline. On the other hand, we measure electrical conductivity. The increase is very limited. That means the water is still fresh water, it's still drinkable. How about costs? The cost analysis tells us we just need 14 cents. We can support one family, one 4-person families. So it's affordable. But how can we use it? Ferret, I see it's purple crystals, like the salts. But how can we dose it into water? How can we remove the particles after treatments? The particles means the iron flux. So we propose the idea that is a tea bag design. We pre-pack ferret salts into tea bags. We can store it anywhere in our house. If we need it, we can use it. If you know how to make hot tea, you can make clean water by yourself. So this is a tea bag of ferret. We add it into water. After treatments, we get water together with iron flux. So we can use coffee filter or paper towel to remove particles before having clean and drinkable water. So that is our design for emergency water treatments with ferret. Next, let me show you the second research area, stormwater treatment. We focus on reusing water industry wastes to remove stormwater contaminants. Because we know water treatment residues and sewage sludge both are wastes from water production and wastewater treatment. This is a big problem for our urban water cycle. Second, stormwater is a major non-point pollution source in cities. So we have two problems, but we try to use one problem to solve another one. I mean, we want to kill two birds with one stone. Water treatment residue, it is iron or aluminum hydroxide. It's perfect absorbent for heavy metal and phosphate in stormwater. We can directly use it. For sewage sludge, we cannot. We have to transform it into biochar before use. Biochar is very, I see it's carbonates the product. It can sequester the carbon in our wastes and mitigates climate change impact. Okay, look at urban stormwater. Number one, urban stormwater is pollution. It contains different types of pollutants, including heavy metals, nutrients, microbes, organic compounds, and salts. For example, like heavy metals. If we collect the runoff from highway, inside it, it has high concentration of zinc, because zinc is from where? From our tire. On the other hand, if we can clean stormwater, we can use the water for drinking water source. Or we can use the water for our gardens, for our community farms. So here, just show you where we produce our waste residues. This is a drinking water treatment flow chart. We produce WTR here. And this is wastewater treatment systems. We produce sewage sludge from secondary settlings here. Every day we produce huge amounts of treatment residues. For United States, water treatment residue, 6.6 million tons every year. And sewage sludge, 4.8 million tons, dry sludge every year. So this the two pictures just show you what water treatment residue looks like. So here we can see this is a fresh WTR after dewatering. This picture was taken in a drinking water treatment plant in Bridgewater, New Jersey. It just waits for transport, for disposal. After totally drying, looks like that. These powders here. We can use SEM to see morphology of WTR, very small particles. The surface here, we can see huge specific surface areas. Similar to sewage sludge derived biochar. Very beautiful, flower-like small particles. The big surface areas on the particles provides the space for reactions, for absorptions. So all the contaminants can be captured on the specific, on the surface area here. Okay, next question is how to use it. We can directly dose it into soil. That's no problem. But the problem is, it's not sustainable. If we dose WTR or biochar into the topsoil, eventually they will be oversaturated with contaminants. After that, what happened? What can we do? We cannot keep dosing, our WTR or biochar forever. So here we proposed a new method for application. We pay attention to wood mulch, because we know that is very common materials for landscaping in the United States. What we did is to coat WTR powders on the surface of wood chips. We make the WTR coated mulch. So see here, this is the wood chips. On the surface, we have WTR coating. So when the storm water goes through it, it can capture lead, zinc, copper, heavy metals, as well as phosphate. From here you can see this is a demonstration unit. We have topsoil here. Above it, this one layer of WTR coated mulch. Above it is a sewage sludge derived biochar coated mulch. So they will provide different functions. WTR coated mulch can remove heavy metals and phosphate, while biochar coated mulch can remove organic contaminants. So look at our benefits. Number one, we do not change the basic functions of wood mulch. We still can control weeds. We can minimize the soil erosion and keep the moisture in the soil. And also, our coating is active. It can remove contaminants. Every spring, we need to, replace our wood mulch. So we have we just have the fresh coated mulch and make sure we have a long-term treatment capacity. It's easy. It's easy to use, and it is low cost because our raw materials, WTR and sewage sludge, they are free, and it's resilient. We can use it alone, or we can combine it with other stormwater treatment systems. For example, biofiltration basins. And also, this is a sustainable idea because we reuse our waste. So here I show the column studies here. We just built the filter bed. So inside we have our coated mulch, and we just end the polluted stormwater. We measure influent concentration and effluent concentration. So the ratio of effluent to influent concentrations is y-axis here. And x-axis is the volume of water to be filtered. And we tested two different filter bed depths. One is 2 inches. Another one is 4 inches. So from this graph, it's pretty clear. Number one, coated mulch is much better than raw mulch to remove contaminants. From this slide, we can see the removal of phosphorus and copper. Number two, if we increase the depth of the filter bed, our treatment is better and more reliable. Similar to zinc and lead. We also extend our research to some other areas. For example, look at this graph. we use sewage sludge-derived biochar to remove contaminants of agriculture runoff. This system was installed at the Montclair community farm. Moreover, we built another system just on the campus. We can see this system is installed on the green roof of CELS building. We collect roof runoff, introduce roof runoff into the big black pipes. Inside the pipes, we have the mixture of sands and biochar. We can remove contaminants, including heavy metals, from the runoff. Okay, so finally, let me very briefly introduce some of our ongoing research projects. Number one, PFAS. PFAS are a new type of emerging and persistent organic pollutants. It's extremely difficult to be removed by established technologies. We proposed concentration and destruction approach. That means we use adsorbent to capture trace PFAS from huge amount of water. So water is clean. And then we regenerate our adsorbents. We have two purposes. Number one, destruct PFAS for detoxification. Number two, we can recover our adsorbents, and then we can use it again to reduce overall treatment costs. But PFAS is pretty stable, so we have to choose strong chemical technologies. That is a new advanced reduction process. We just use the most reducing agent, that is a hydrate electron, to destruct PFAS from toxic to non-toxic chemicals. Another research is household water treatment. I just mentioned we used ferrets for emergency water treatment. From that project, we have been more and more interested in sustainable design of household water treatment products. It's important. Why? Because 2.2 billion people in the world need household water treatment. Most of them are living in developing countries. For the United States, actually, more than 1.1 million people also need household water treatment. More than half of them, actually, they are living in metropolitan areas in this country. So very recently, I proposed 5 key principles for design of sustainable household water treatment. Number one is treatment capacity. That's about technology. How can we remove traditional and emerging contaminants while minimizing formation of disinfection byproducts? Number two, how can we minimize environmental and energy footprints? That is a green technology. Number three, user experience. People always like the easy treatment methods because very different from our municipal water treatment. The operators are underusers. So we need to develop some easy and simple products for our end users. Next one is cost. Cost is always issues for us to choose our products. That is a key issue for people living in low-income countries. Last one is social acceptance, including public acceptance and market adoptions. Also, we highlight the interactions between the 5 components. For example, if the system's treatment technology is performed well, if the cost is lower, if the system can be easily used, so our social acceptance will be what? Will be enhanced. Another project we are working is water reuse. We combine ferret technologies with constructed wetland. we treat municipal wastewater to produce water for irrigation, agricultural irrigation. So that is a collaboration with Egypt scientists. Okay, endless challenges. We know over the past years, the largest challenge for us is virus, COVID-19. I believe over the past year, you have frequently used disinfection. For example, this picture just shows you, the people just disinfect the streets to kill the virus. But on the other hand, we just think if intensify disinfection brings some negative impact on our water quality. Very recently, we published one paper to discuss the potential negative impacts. We see overuse disinfection also can poses potential risk to water quality, particularly formation of toxic disinfection byproducts in our drinking water source. So finally, I greatly appreciate support from different funding sources, including federal agencies, non-profit organizations, and industry sector. I'd like to save the best for last. I greatly appreciate all the group members, including my PhD students, master students, and undergraduate assistants. Also, I appreciate my postdocs, visiting professors, exchange students, as well as high school students who did summer research intern with us. Without their hard work, I cannot achieve anything. Finally, thanks for your attention. So my presentation just stopped here. Thank you.